And then I'll change the spotlight also, which I might have to come here. Yeah.
Thank you so much. Perfect. So I'm very glad to introduce Ludovic. So Ludovic, Professor Ludovic he's an associate professor at Sorbonne University in France. And he's an expert in post-quantum cryptography overall, both in theory and practice, as he will talk in this session. So Ludovic is a personal collaborator of mine, and he has so many papers in this area, and he is also working in industry, has worked in a startup, and he has a lot of different aspects, both in cryptanalyzing and also designing new primitives. So he's definitely an expert in this transition that the world is moving towards post-quantum, and I'm very happy to have him here. So thank you very much, Ludovic, for accepting, and the stage is yours. Thank you.
Thank you, Daniel, for the introduction, and good morning, everybody, or good night, depending whether where you are. So as you mentioned, Daniel, so I work since quite a while on post-quantum cryptography. So just to recall, so it's a set of crypto systems which are supposed to be secure against a quantum computer, but do not forget that they have also to be secure against a classical attack. And I am working on this area since quite long, and not only as an academic, but also I move a bit on the industrial part, doing a startup. And in between the two worlds, I was quite involved into standardization and also deployment of post-quantum cryptography. And so as of today, I want to show and to discuss two of the challenges that I believe that are very important today for post-quantum cryptography. And the first one is how to assess the security of post-quantum schemes in general, and in particular against a quantum adversary. So I will show you some results in this direction. And so the second point that I want to discuss with you is about the challenge of deploying post-quantum cryptography at scale. And for that, I will say that I have no definitive roadmap to propose you, but just some kind of general remarks on how to make this transition. And so the context of on which this work occurs is quite well known since many years. So I guess you are probably all familiar with the fact that if there is a large quantum computer which is going to appear, then current public key cryptography is going to be broken. And broken means here quite bad, since that with something which is supposed to remain safe for centuries with classical algorithm will be broken in a few minutes. And actually the algorithm is polynomial time, so there is no easy way to tweak RSA or Diffie-Hellman. You have to change to something different, so which are post-quantum schemes. And the impact, the practical impact is quite huge because basically public key cryptography is almost everywhere. And so if you kind of have a deeper look, typically for a bank, so you will have public key basically for three different stakeholders. So of course, now we are all a mobile application for managing our accounts. So first issue is with all mobile banking application. So banks also have to deal with third-party financial parties, and so communication with respect to them has to be secure. So we can think about central banks as well as kind of backbone financial network like SWIFT. And in addition of that, as all large companies, so you have to manage corporate data, so you have to secure them. And so once, if you have no longer public key cryptography, then you are basically going to be in trouble. And so this is the global picture, which is quite the same since about 20 years. So what changes in the last 5 years is that the possibility to have a powerful quantum computer is appearing to be more and more plausible. So we don't know when a large enough quantum computer will appear at this stage. Some people believe that it will be in 20 years, 15 years, maybe they are some aggressive. Some of them say this is never going to happen still. So we saw astonishing progresses in the last years building such quantum computers. So we heard about the Google experiments, which was the first non-trivial, still theoretical application of quantum computer, which shows that you can do something faster in the quantum settings than in the quantum setting. And so IBM published a roadmap saying that, well, in about 1 year from now, we will have more than 100 qubits. And so knowing the state of business for a quantum computer 15 years ago, this is quite impressive. Still, the amount of the power needed, the number of qubits needed for actually breaking a real cryptographic application is much bigger than that. So the issue is that qubits are not perfect, they are noisy, so there is some errors. And so if you want to run something extremely complicated like a Shor algorithm with the current technology, you will need a large amount of qubits to attack something which is used today. So in one hand, things are progressing. On the other hand, we have to be aware that we are very far from being able to break classical public key cryptography. So one should wonder why we need to take into consideration this threat at all, because at this stage the risk seems not here. And in fact, there is one reason why probably now we are moving to post-quantum schemes is due to this time bomb effect. So maybe the issue is not here today, but probably in several years, we are going to be able to decrypt data with a quantum computer. So the point is that storing data is quite easy. So we can harvest at scale and data at scale and decrypt them later once you have a powerful quantum computer. And so for data which have long life cycles, let's say 10, 15 or 20 years, well, this is a big issue. So that's why NIST, about 5 years ago, decided to standardize new public key schemes. And in particular, they want to have post-quantum schemes. And so one of the fundamental assumptions in the post-quantum setting is that there is new hard problems which are different from factoring or discrete logarithm that are secure in the quantum setting. So here are the 5 kind of schemes which are usually considered as the one which are secure against, which are assumed to be secure in the quantum setting. And so in the first part of my talk, I will focus on one generic technique to assess the security of such scheme through polynomial system solving. And so I will show you how we can boost polynomial system solving using a quantum algorithm. So this is going to be the first part of my talk. So polynomial system solving is relating to security of a large variety of schemes, including post-quantum schemes, through a generic method which is known as algebraic cryptanalysis. So the point is that you can always model as a crypto system, let's say a post-quantum crypto system, as a set of algebraic equation over a finite field. So this is the POSO problem that I mentioned here. So this is a modeling scheme, modeling step, which is, as I said, always possible because due to NP completeness of POSO. So the second step is to try to solve this system that you generated, which will give you some relevant information about your scheme. So the message associated to your ciphertext or the secret key. And so this means that the hardness of this POSO problem is fundamentally related to the hardness of most of these post-quantum schemes that I mentioned before. So that's why I got interested to this polynomial system solving problem, and I will show you how we designed a fast asymptotic quantum algorithm. So the problem is as follows, to be a bit more formal. So you have a set of nonlinear equations over a finite fields. For the moment, it's over FQ, and after I will specialize over F2. And so the question is to find a vector, an assignment, which will vanish simultaneously all this equation. So if your equations are linear, then it's easy. Once they become nonlinear, which is the case here, it's difficult. And so here on the input, you can see that there is no bound on the degree, but if you fix the degree to quadratic equation, which is a case of interest for crypto, then the problem remains difficult. And so in what follow, I will only consider polynomial system solving for quadratic equation over F2. So what is known about the complexity of solving this problem? First, in the quantum setting. So first, there is a quite precise estimates on the cost of solving a POSO with exhaustive search. So this is almost the exact number of operations that I gave here. So there is no big O. So the best asymptotic algorithm is quite recent. So as I can mention, so the field of polynomial system solving is still dynamic, and this algorithm is currently the best algorithm that you can find for solving POSO. So it's an asymptotic algorithm, and there is a lot of hidden factors which are hidden in this notation O star. So during a long time, the best algorithm was Boolean solve, and which combine Grobner basis computation with exhaustive search. And this is the algorithm that I'm going to be interested on, and I will show you a bit more details on that, because what I will show you is a quantum version of this algorithm. So one difference between Boolean solve and the polynomial approximation algorithms that I mentioned is that we will need some assumption on the system to derive this complexity. And so I will explain where we need this assumption. And so on the contrary, there is, so this polynomial approximation is the worst case algorithm, so there is no assumption. So I'm interested in mostly in improving the state of the art in the quantum setting. And so there is, as far as I know, two quantum algorithms for solving Boolean polynomial system of equation. So the first one is a quantum exhaustive search and use Grover algorithm, so which give you basically a quadratic speed up on the complexity. Another algorithm, which was due to Chen and Gao, reduce system solving to a certain linear algebra problem on which you can use a fast quantum linear system solving algorithm, which gives you an interesting complexity, which is polynomial in this kappa number. So it's a condition number which is associated to a certain matrix. However, it appears that this number is exponential in the Hamming weight of the solution. So in fact, this algorithm is no longer, is not better than quantum exhaustive search. So the challenge now is to design an algorithm which beats quantum, which beats Grover-like search. And so in the papers that I mentioned before, on saying that on the assumption that there is some problems which are interesting in the quantum setting. So there is this paper of Bennett, Bernstein, Brasser, and Vazirani, which shows that if you consider your problem as a black box, so the best speedups that you can for quantum algorithm is the one which is given by Grover algorithm, which is a quadratic speedup. And so there is one theoretical limit, but this theoretical limit states that, well, use the fact that you have a black box access to your problem. And so in fact, by taking into account the structure, I will show you that we can have better than a quadratic speedup for this problem. So let's first go through this Boolean solve algorithm that I describe in the classical case, and after I will explain how I can do a quantum version of this algorithm. So there is two key ideas on this algorithm. So the first one is that you will mix two different techniques. So you will combine something that I call a Grobner basis-like computation with exhaustive search. And to be more precise, it's here you have here's algorithm. So I have some parameter k, which is smaller than the number of variables. And so I will do basically two steps. So I will first specialize a part of my variables. I will check the consistency of this problem. So I mean, I will check if this system, once I have specialized A inside, as a solution. And so this is the Grobner basis-like computation that I mentioned. And in fact, it's a linear algebra computation which can be done in quadratic time. So it's my first step, this linear algebra step for checking consistency on a smaller system. And so the second step is to find the remaining part of the solution. Once I know that my system is consistent for some guess value A, I will do just some exhaustive search to find the last part of my solution, so which will give you a solution of my system on P. So let's see how I can do this consistency check and how I can reduce my problem to linear algebra. And so the reduction is done through this. Yes?
By consistency, you mean that there exists a solution, right?
Yeah, that there exists a solution, exactly.
Okay.
So to do this, to check that my system has a solution, I will reduce to the problem to checking that a linear system is consistent. And for that, I will consider the Macaulay matrix of my polynomials. So the Macaulay matrix of my polynomials, of my initial system, is defined. The rows are going to be multiples of my initial polynomials. So sorry, this should be a P here. So the rows are multiples of my initial polynomials, and so the columns are just the coefficient of my monomials up to some degree bound D, which are sorted with respect to some monomial ordering. So it's just a way to compare non-ambiguously all my monomials. So I map in this way my polynomials to Macaulay matrix up to some degree. And so one of the results that you can show on this Macaulay matrix is that, in fact, you can reduce the problem of checking the consistency of your nonlinear system to checking the consistency of a particular linear system, which is basically essentially constructed from my Macaulay matrix. So this is my linear algebra step. So I reduce my checking, a nonlinear problem to a linear algebra problem on my Macaulay matrix. So I know that for, and it's important, for D big enough, I have this equivalence. So that's a way where I can do consistently check. And so after I have to do a linear algebra, so I have to check the consistency of my system. And so this is the trick to do it in quadratic time for doing this particular task of checking the consistency of my system, which you can prove it's sparse enough. Then you can do it essentially in quadratic time in the size of your matrix. So that's the classical case, the part which was existing already. And so what I will show you is that we can quantumize this algorithm using the Grover algorithm. So Grover algorithm is given here. So it's a quantum algorithm which allow you to find some x star such that f of x star is equal to 1. And this can be done faster than exhaustive search and quadratically faster. And so the algorithms that I mentioned, in the state of the art, doing a quantum exhaustive search exactly use this Grover algorithm. And so the function that is given to the algorithm is this f is just the evaluation of my polynomials. And so my function f, in this case of doing exhaustive search, they will only returns 1 if x vanish all my polynomials. And so one point that you have to take into consideration in Grover algorithm is that to get this speed up, this function f has to be implemented not in a classical circuit, but as a quantum circuit. And so here, you need to implement evaluation of a set of nonlinear polynomials on a quantum circuit. So which is not theoretically difficult, because we know that everything which can be done in the classical setting in polynomial time can be done as a quantum circuit, but you need some additional properties. But this can be done, but we have to take this into account, that you need to implement the function on which you do a Grover as a quantum circuit. And so this is the quantum algorithm that I give it here to you. So it's the second one, and I put also the classical one in parallel. So we are going to use quantum Grover-like algorithm in 2 steps. So the first, most obvious one is on the second part, because, well, so it was just exhaustive search, and so you just do the Schwabe-Westerban quantum algorithm for doing that, which is basic quantum algorithm. And so the trick, and what makes actually the algorithm fast, is that you can use also Grover algorithm for the first step, because it's also like a Grover-like problem. So you want to check that it is consistent. So you have a function f on which you want to find some a such that this is consistent. And so you can use typically a Grover algorithm also in this part, but you need to implement the linear algebra step that I mentioned before as a quantum circuit. Anyway, this can be done, and so after we can do the exhaustive search. So I just give here the high-level idea of this algorithm. It's basically the same algorithm that we are doing in the quantum setting, and the same type of assumption. And the main difference is that instead of having 2 to the k for the exhaustive search, you are going to have divided by 2 because you do Grover. And so this is actually the cost only of the first step of doing the consistency check. So, and we can prove that in fact the cost is mainly given by this checking of consistency of your nonlinear system. And so you have this quadratic speedup for the first part. And so this is essentially the cost of performing the linear algebra part on your Macaulay matrix. So this is the 2 of the linear algebra, and 2 to the f gamma alpha is in fact the cost, in fact the size of the Macaulay matrix that you have to consider. And so yes,
you have 5 minutes. Yes,
okay. And well, 5 minutes, okay. and using some regularity assumption, actually you have a precise bound on the maximum degree that you have to consider for your Macaulay matrix. So, and once you do all the computation and you minimize the function, then we get the faster current algorithm for solving POSO. And well, interestingly enough, well, you get some speed up, so you beat basic exhaustive search, but probably you can hope to have something which is a bit faster. Okay, so let's go to the second part of my talk, which is about actual deployment of post-quantum cryptography. And so the first observation is that, well, of course, standard is a first step for this deployment. And so recently NIST announced the first winner for the standard. So it's a first step of standard because actually the process is ongoing. And so there is an additional round for key exchange and also a new call for digital signature by next year. Still at this stage, we have no post-quantum algorithm that you can start to deploy. And so, of course, a standard is not a mandatory, but the actual trend is that you have more and more regulation. And so regulation is coming. So typically the White House issue a set of memorandum of understanding, basically asking all the industry and public administration to prepare their transition to a quantum resistant cryptography. And it's quite aggressive. And so even more recently, NSA announced an update of their commercial national security algorithm, already including post-quantum algorithm. And so just, I would say for an industry like bank and financial sector in general, the question is not whether you have to do this transition or not. It's almost mandatory. The question is more when and how to do this transition. Actually, for all, there is already a timeline which has been issued by NSA. And so you can see that they asked for starting to do this transition quite soon. And for some particular application, typically a networking equipment. So they asked to start in about 2 years, and for a software update about next year, with a deadline which is going to be in about 8 years. And knowing about the challenge that you have to solve for doing this transition, this is not going to be a lot actually. And so this question of how to do this transition and what are the recommendations that you can give to industry, it's, I would say at this stage, widely open. And so that's why I recently started a standardization group exactly on this topic, trying to give some guidance for doing this transition. And so maybe I will just focus on, and this is almost my last slides, about how to implement the post-quantum transition. And I would say it's not only about implementing a post-quantum algorithm, it's about to prepare your IT infrastructure to be agile. And so agile means that your ability to upgrade from a potential weak crypto primitive to another one. So the work that has to be done is not only for post-quantum, but for any cryptographic algorithm in general. And so as Yassir Nawaz mentioned 2 years ago, doing this crypto agility is probably the path that you have to follow, but there is a lack of guidance for doing this transition. This is kind of moving a bit, so the literature is improving. So, typically you start to have guidance on software agility, on crypto API, that your API should be agnostic about the actual algorithm and only provides the functionality. So there is also some agility that is possible at the protocol level, but you have to be careful. And so typically in the post-quantum setting, the recommendation is to implement hybrid. So you not remove completely your legacy crypto, you add a post-quantum or any new algorithm as an additional layer. And so I think this is almost the end of my talk. So, and in the financial sector, it's even more complicated because you have multiple stakeholders to upgrade in parallel. And your cryptography is not only managed internally, it also managed through products of external vendors. Still, I believe that probably the financial sector is going to be the leading industry for doing this post-quantum transition, because until now it's probably the industry which is the most dynamic in this setting. And I mentioned here as a conclusion some research topic that will have to be addressed in the future, and maybe just to one. So first, we need some tools for helping in this transition. So typically, in how to discover the cryptography that you are using. Another topic, well, which is in the scope of this workshop, is that at this stage, multi-party computation is a vastly open question for post-quantum cryptography. So we are starting to see some new results, but this is only an area which is starting.
Okay, Ludovic, thank you very much. Maybe just one quick question, if there is any, before we go to break. Okay, maybe if you can be very prompt, yeah. But can you come? Okay, of course.
So first, I'm quantum student of quantum physics from US Bank. So the first question is why you didn't consider like Shor algorithm instead of proof algorithm? And the second question is we, from the experimental point of view, don't see what's your recommendation. Is it going to be like a quantum annealing or just the universal? I know you should mention post quantum, but is it going to be universal or annealing, quantum annealing? And the third point is third question is that question is actually, if you think of it as a discussion, like I feel like it's a approximation problem in the NP hard, and I feel like the quantum annealing is best approach for approximation problem.
Yeah. Ludovic, did you hear the questions?
No.
Yes, of course. I mean, so yeah, the first one was about Grover, right? So what did you use? Shorts. What did you use Grover and not Shorts?
Well, so we use Grover algorithm in our context because it was well suited to do the tasks that we want, because it was basically an amplitude amplification problem, and so you want to find a solution, and you want to inverse some function. So it was well suited for the tasks that we want to solve. And so Shor algorithm is for factorization. Well, so basically is for doing a period finding, so the quantum part. And so at least we did not see how to use Shor algorithm in our context. And so I think it was a bit more clear how to use Grover algorithm.
Can you repeat the second question? I can relate.
Okay.
One was about the approximation.
Yeah, can you tell us like what the best implementation for this approach? Is it I know you mentioned post quantum, but is it the universal or is it quantum?
Oh yeah, like can you expand on the best implementation of your approach?
Which approach?
So your solution. You mentioned post quantum. Yeah, you use a universal quantum circuit, right?
No.
Yes.
For the quantum circuit implementation, universal quantum or quantum annealing?
Okay, for the quantum circuit implementation, yeah, is it a universal circuit or like quantum annealing?
So yeah, I think I kind of heard this part. So yeah, we use a universal quantum computer. Indeed, and yes, it makes sense also to consider a quantum annealer as well, but not exactly for what we want to do. But so there are some techniques which allow to reduce polynomial system solving to a minimization problem that can be well attacked with a quantum annealer. So one of the issues with the quantum annealer approach is that they are very heuristic. So most of the time it's difficult to understand what is the complexity. But yes, indeed, it could be possible to also consider quantum annealer to try to solve this polynomial system solving problem.
The last one was about approximation.
Yeah, he actually answered the same question.
Oh, okay.
It was about quantum annealer.
Okay.
I'm not a big fan of quantum annealer, but I agree.
Okay. Thank you very much for the discussion. And since there are no more questions, let's thank the speaker again. Thank you, Ludovic. And we're coming back at 10:30. We're moving the schedule a bit. Thank you so much.